Welcome to our Parallel Programming Concepts course. This week we talk about accelerators, and we already seen how to program for accelerators and that there are a variety of different types of accelerators. And now we see how we can not even get good performance, but even better performance with accelerators, and what kind of optimizations are there in order to really get the maximum of the power of the GPU. We've seen this example before, where we had a Sudoku validator that actually created a very big Sudoku field and then checked if the Sudoku field was correct or not. And we've seen that we had big performance gains for pretty big problems. But if we increase the amount of the problems even further, we see that the GPU is almost as bad as the CPU. So the AMD GPU almost has the same curve as a CPU, and the execution time gets really larger. And also with NVIDIA GPU, we get worse if we increase the problem size. And actually, we want to have a very good execution. So this is what you usually see. Getting stuff to the GPU is pretty easy, and then it's pretty fast as well. But if you increase the problem size further, performance will go down then again. And with the optimizations that we see here, you can really get good performance there as well, and also in the beginning. So what are the optimizations that you can look at? First of all, so this is a summary of the best practices for performance tuning for accelerators that we found. And first of all, one fundamental difference with GPUs is that since memory wall is coped by with this memory latency hiding, another way of dealing with this would be recomputing stuff. Instead of looking it up in the memory, you could just recompute the value. And all the threads are doing this in parallel, so that doesn't really eat up so much time as compared to looking the value up. So sometimes it's a pretty good idea to not store the results of something, but to recompute it. Although there's a vast variety, a vast amount of registers on the GPU, they are still crucial, and if you can free some of the registers, you can store more thread there and do more parallel computation then. Another thing is we learned before that you always have to copy the data to the GPU, then do the calculation, then copy the results back. This is usually pretty expensive. So if you look at GPU programs, then for very small problem sizes, they have a huge overhead just for this copying stuff from one side to the other. And you can kind of reduce the burden of this if you copy the data there once. Then you execute different kernels, one after another, on the GPU, and then you copy the result data back. So instead of copying it there, running the first kernel, copying it back, then copying it there, running the second kernel, copying it back, you can leave it on the GPU and have different kernels working on this. This is called chaining. Or you could deal with this memory transfer by copying only a part of the data there, then starting the computation on the GPU, and while it computes, copying the next part there, because the GPU can actually transfer data and working on the data in parallel. Then control flow, we learned that branching is usually not such a good idea. So if you can reduce the amount of different branches, then this will be helpful for a GPU as well. And one special case of this would be to, instead of having a loop, doing some unrolling mechanisms in order to reduce the amount of variety in that loop. And this may lead to some threads doing stuff that they actually don't need to do, but this is usually a better idea for GPUs because all the threads are doing the same anyways than having clever branching optimizations. Clever branching optimizations, on the other hand, are pretty cool for CPUs. So they bring good performance for CPUs, but on GPUs they are not such a good idea. Also, you should take into account that between different work groups, branching is allowed. In one work group, though, having branching is really a burden for the execution. Then we learned that there are different memory types. For example, a local memory that is basically a cache that you can use yourself and manage yourself. And you should really make use of this because it's way, way faster than having the standard memory of the GPU. And there's a lot of examples how to use this memory, and it's really not that hard. Accessing the memory is something that was very, very crucial in the past. So if you did the wrong pattern of accessing the memory, that was really a big burden for your performance. Today it's not as bad anymore, but you can still think about this, and we're going to look at some examples very soon. Then we've seen that there is this big index range, and you actually can subdivide the index range as you like. So you can have very small work groups or very big work groups. You can have it one-dimensional or two-dimensional, and usually you don't really know what is the best idea. Also, you could have like bigger threads doing multiple tasks, or like bigger tasks doing multiple work at once. Or you can have very small tasks. Usually for GPUs, it's a good idea to have very, very small tasks, doing only one thing at a time and then finishing. But sometimes it may be beneficial to have like having 4 things in the same task, because then you have a smaller overhead for scheduling this. And the sizing of the work groups is also something that you don't really know upfront. So sometimes it's a good idea to just play around with this. Try larger ones, try smaller ones, and look at what is happening with your performance. Then we have different instructions. So we have vector types, as we've already discussed. Sometimes it's also good to use shifting instead of multiplying by 2 or dividing by 2. GPUs have some special functions like fused multiply, where you can add some values and then multiply another, and this is actually done in hardware and way faster than doing a multiplication first and then doing an addition. So you can use this fused multiply call in the library instead of using like multiply and add first. And also, if you can cope with a lower precision, you can use native math functions like hardware implementations of Thinus calculation or a square root calculation, which is very fast on the GPU but has not the same precision as you would expect on the CPU. And also, there's some built-in options where you can just say all the double precision values that I send you are actually single precision values, and you can deal with them as if they were only single precision. Then you can get a really good performance speedup on the cost for precision again. And we now will look into this a little more in detail. So divergent branching occurs if you have an if statement, a switch statement, a do, for, while statement. And this leads to different execution paths. And this is something that you really want to get rid of. You want to have them all do the same thing. Because otherwise, the GPU will use predication. And predication actually means that all the threads are doing both parts of the branch. And then it's just marked which execution results should be really stored back. So if you have an if statement, both parts will always be used. If you have a switch statement, all possible branches will be executed by all threads. And this is really a huge amount of additional work that you actually don't want to have. And unroll loops by yourself or using Pragma Unroll from NVIDIA will help you to reduce problems with loops, where sometimes a thread is really fast exiting the loop and others are longer inside the loop, and also all this managing of the loop variable that is increased all the time. You can get rid of this a little bit by unrolling the loop. So this is usually a good practice to deal with branching. Another thing is we've already heard about the local memory that is way faster than the global memory, and you can manage it yourself. It's pretty small though, and you have to think about what to put there, but still this is one of the fundamental ways of speeding your GPU application up by using this cache cleverly. In addition to this, we have 2 memories that are interesting. The first is the texture memory, where we have 2-dimensional caching. So if you have a 2-dimensional problem, it's usually a good idea to use texture memory to express your problem. It's still like a normal array. You can access everything as you are used to using arrays, the only difference is that it's read-only, and if you access an item, then the items around this item are cached as well. And this is pretty beneficial if you have to access them afterwards anyway. And also, as I said before, the border parts, if you access an item that is behind the border, basically, which is usually the case if you look at all the neighbors and you have the top left item, for example, then some of the neighbors would be outside the array, right? You can deal with this in texture memory, and then even your code looks more beautiful because those special cases are handled by the infrastructure already. And in addition to this two-dimensional cache, you also have a one-dimensional cache, this constant memory, which is a linear cache. It is also read-only. It's pretty small, and a good way of using this would be to put the input parameters, for example, there, because all of your threads are going to have the same input parameters, and usually you just read them anyway, and then they don't need to put them into registers, but they can use the constant memory in order to access those. And the constant memory is roughly as fast as registers because it's also on the same chip. But so you can free up registers for other tasks. And registers can be written to and constant memory not, but if you don't need it to write to this, then it would be a waste, right? Then I was talking about right sizing before. Usually it's a good idea to have a workgroup that is a multiple of the native execution size. And the native execution size is 32 with NVIDIA, 64 with AMD, and with those mix, it's 16. And if you have a large workgroup, then this allows you to have all the communication between the work items in that workgroup. That may be beneficial for your algorithm, but on the other hand, so you can only store so many large workgroups on a multiprocessor. And as I said, they want to have a lot of threads there. And every time one of those workgroups is accessing memory, then the workgroup basically will be put away because it waits through the results, and then they would like to, the multiprocessor would like to take another workgroup to do the next calculation. And if you have really large workgroup, then you are only able to store 2 of those on the multiprocessor, and then you cannot really use the memory latency hiding mechanism as good. So in contrast to this, if you have small workgroups, then you can benefit from memory latency hiding because all the time a workgroup is accessing memory, they can just put the workgroup away and have another workgroup executing. But then if the workgroup is smaller than the native execution size, then this means that although your CPU could execute 32 threads really in parallel in hardware, if you have only 5, then 27 will not be used. So 27 threads that you could execute are not executed. And this is the reason why it's usually a good idea to have a multiple of the native execution size so that you have enough threads that they can be executed. And on the other hand, you have small workgroups so that you can just shift them around and use memory latency hiding. In addition to this, sometimes it's really good if you have a 2-dimensional problem, for example, or a 3-dimensional problem, to use the layouts, to use a 2-dimensional layout of your ND range so that caching is better and also accessing the data is more beneficial to what the GPU would expect and is actually doing. So you should just experiment with this, experiment with the sizes of the workgroups, experiment with the layout, and measure the result, and then choose one that's very fast in your particular case. There are some special instructions that you can use. Single precision floating point add and multiply add. A GPU can do 8 of those operations per cycle. So if you really can cope with smaller precision, then using these functions is a pretty good idea. Also square root or logarithm or sinus and cosinus. GPUs are really fast with those kind of things because they need those for all the graphical tasks anyway, and they have special function unit that can deal with this very good and very efficiently. And you should really think about using this if precision is not as important for you. Also, dividing is very expensive. Modulo is very expensive. That holds for CPUs as well. And then having shift operations instead of using those is usually a good idea. If you can deal with smaller precision, you can also use those compiler flags. Then a lot is just done by the runtime for you, and you don't have to think about this. And there's also a number of other library functions that you can use in order to get faster. The one thing that I mentioned before is this coalesced memory access. This was a very huge problem in the past. Today it's not as bad anymore, but still. And the idea here is that since you have your indexes, threads that are executing your work items are accessing cells in the memory then, and they can access the cells, for example, in the way that we see in the first picture, where everybody is basically accessing the cell that is next to each other, and they are some thread that did another branch, for example, and are not accessing the memory. This example below, above, could be executed in one memory fetch, which is pretty cool, which is pretty fast as well. So all the threads will get their data by just one memory fetch. If you permutate this, modern GPUs can deal with this as well, and it's still one memory fetch. Old GPUs would have a problem here, and you would have one memory fetch for each thread, so 16 times, for 16 threads, it would take 16 times as long, which is pretty huge. Then you could also have execution where you are not in the same segment, and then this could be still pretty fast with modern GPUs or pretty slow with old GPUs, and you could also have like spare parts that you are not accessing in the memory, where the first thread is accessing the first cell and the second thread is accessing the third cell, and you have those spare parts in it. This is good again today, but it was very bad in the past. And if you work with old GPUs, you should think about all those memory coalescing problems, and they are all in the guidelines, so there's good understanding of what you can do here. But for modern GPUs, it's not that hard anymore. One thing that I wanted to mention as well is the Intel Xeon Phi, or MIG processor, since we talked about this before. Here it's a good idea to have a lot of workgroups, as with GPUs as well. And each thread of the Phi is actually executing one of those workgroups. And since we have 240 hardware threads, it's again a good idea to have a multiple of those, like 480 or 960 threads, workgroups that can be executed by threads then. And one interesting behavior here is that the most inner loop that you have in your code, like if you have the example below where you have 3 loops, the most inner loop is always used for the SIMD execution. So you want to make sure that the most inner loop is always iterating in a way that multiples of 16 are executed, because then it fits into the 16 elements that can be sped up by the hardware basically, and this will lead to good results. If you don't have a multiple of 16 there, then this will really lead to not so good results. For this most inner loop, there's a number of optimizations that are important, or things that you have to keep in mind. And the first is that branching again is a problem here. So you can branch in the rest of the code, but if you work in the most inner loop, then you should get rid of branching, because this again hinders your performance because it's executed in a SIMD fashion. And also, you should make sure that everything is in a vector that is a multiple of 16, so that the SIMD units can really be used in order to do the execution. and you need to have a linear exist pattern because otherwise SIMD is still, or the SIMD execution will still be a problem. So this coalesced memory problem that we've discussed also applies here. And if you want to know more about MIG optimizations, MIG is a pretty new system, and there are some works out there like the one below, but there's still not so much to be found because it's actually currently researched. And since we are talking about current research, anyway, this is the next lecture where we talk about future trends and what people are currently working on and what you will see in the future, where all this accelerator stuff going to.